Right, let's talk about touch flow conjectures. So built-up made beautiful conjectures on nowhere-zero flows, which is highly non-trivial. So far, all these three problems are open. So the first conjecture is touch 5-flow conjecture. In 1954, this conjecture states that every graph with no cut edge has a nowhere-zero 5-flow. Okay. So what's the point? Well, we know this easy theorem that every planar graph, every loopless planar graph is 5-colorable. Right? We know the proof by using Euler's formula or by using Karsten's list coloring argument. So every planar graph is 5-colorable. So this is true for plane graph, right? Because plane graph without cut edge has nowhere-zero 5-flow if and only if its geometric dual has 5-coloring, which is true. So this is true for planar graph. And this conjecture says that actually for nowhere-zero flow problem, you don't need any number higher than 5. You just need 4 different values, right, to make nowhere-zero flows. So this is completely different, right? For graph coloring, there are graphs whose chromatic number is arbitrarily large. For nowhere-zero flows, as long as you have at least one nowhere-zero flow, let's say by having no cut edge, then this conjecture says that you will always have a nowhere-zero 5-flow. And this is still open. Let me just put question mark. Second conjecture. Okay, so second conjecture is 4-flow conjecture. This was proposed in 1966. So every graph with no cut edge, because if you have a cut edge, you don't have any nowhere-zero flows. You don't have any. So if you have a cut edge, then in any circulation, this cut edge will have value 0. So there will not be any nowhere-zero flows. And with no minors isomorphic to the Peterson graph, so Peterson graph is the graph that looks like this. It's 10-vertex graph. You may have seen it from homeworks. Has a nowhere-zero 4-flow. Again, this is very strong conjecture. Why? Because this is again true for plane graph. Why? But plane graphs will never have a Peterson minor, because Peterson graph is not planar. Right? When you contract these 5 edges, you have a K5. So this is not planar. So planar graph will not have a Peterson graph minor, and as long as they have no cut edge, then this conjecture claims that it has a nowhere-zero 4-flow, which means that in the geometric dual, you have a 4-coloring. So the 4-coloring, the theorem that planar graphs are 4-colorable, implies that graph with no cut edge, implies that 4-flow conjecture is true for plane graphs. Right. And it's known, let me just add a remark. It's known to be true for irregular graphs. So if graph is irregular, then we know that having Nowhere-zero full flow is same as coloring edges by 3 colors. And this was proved by, I think it's Robertson, Seymour, Sanders, Thomas. Right, yeah, in 1990s. Yeah, I mean, they announced the proof. I don't think the proof paper is out yet. All right. So that's full flow conjecture. Yeah, so Robertson, Seymour, Now let's talk about the 3-flow conjecture. That's 3-flow conjecture. This was proposed in 1972. This conjecture said that every 4 edge connected. So far, graph without cut edges is almost same as graph with 2 edge connected graphs, right? In every component is 2 edge connected, except the component with a single vertex. But this 3-flow conjecture says that every 4 edge connected graph has a Nowhere-zero 3-flow. So what is the motivation? There's a theorem called the Conjectures. I don't know how to pronounce it properly. There's a theorem for planar graphs. So this says that every simple triangle free, meaning no induced subgraph isomorphic to K3 graph is 3-colorable. And this is the motivation to propose 3-flow conjecture, because if we have a triangle, then in the geometric dual it corresponds to the 3-edge cut. Right? Inside is separated from outside by 3 edges. So by making 4 edge connected graph, you will never have a triangle. Right? Alright, so here we have 3 beautiful conjectures. All of them are open. But there have been partial progress. Okay? So here we have 5-flow conjecture, 4-flow conjecture, 3-flow conjecture. These are all open. Okay. So I will show you this very nice theorem of JJ in 1975, which says that every 4 edge connected has a Nowhere-zero full flow. So this number 4, if this was 3, then this proves that's 3-flow conjecture, but no, it's 4. So it's slight weakening of JJ's, 3-flow conjecture. Also, in the partial case of 4-flow conjecture, as long as you have a high edge connectivity, you have a Nowhere-zero 4-flow. So any counterexample to Nowhere-zero 4-flow conjecture will have a edge cut edge cutoff size at most 3. Right. So to prove this, I mean, actually, if you look at this judge's paper, then the proof is only a few lines. And we use this theorem by Nash-Williams. In 1961. This theorem states that so let's k be an integer, then every 2k edge connected graph has k spanning trees, t1, t2 up to tk, such that when you look at the distinct spanning trees, they have no common intersections. Okay? And I wrote it in blue because I'm not going to prove it. There's a graph theoretic proof. There's a proof by graph theory, and I remember that a few years ago, one German undergraduate student actually wrote a new proof using only graph theory. So you may try. You can try to find the new proof. The only annoying thing is that almost all graph theoretic proofs are quite complicated. I mean, it's longer than a page normally. Dister's book also contains the proof. I mean, the reason why it's annoying is that there is a beautiful proof by using Metroid theory. So if we have time in the later, we may cover a little bit of Metroid theory, depending on the speed of this course. If you use Metroid theory, there's some theorem called Metroid union theorem, which is also done by Jack Edmonds, the same person who did the matching theory. And if you use that theorem, this is one line corollary, and that theorem has very short proof. So if you want to have a shortest possible proof of that, we need a Metroid theory. We need to go out of the graph theory. So that's why I normally don't show the proof, and if I have time, I will show you the proof by using Metroid theory later. All right, so this is an interesting theorem that if you have a high edge connectivity, you can find many edge disjoint spanning trees. And converse is also true. If you have many edge disjoint spanning trees, then between any pair of vertices, you can find many edge disjoint paths. First pass through first spanning tree, second pass through second spanning tree, third pass for the third spanning tree, etc. So in a sense, this is like a rough characterization of high edge connectivity, right? So if you have a graph with a huge edge connectivity, you can always find many edge disjoint paths, and having many edge disjoint paths already certifies high edge connectivity by factor 2. All right, so let me show you the proof of ZZ's theorem. And Nash-Williams was a professor at the University of Waterloo in Canada, where the Tutt was also a professor. And okay, right. So let's start with the 4-edge connected graph. Achieve a 4-edge connected graph. Right? So the goal is to find the Nowhere-zero G2 times G2 flow. Remember, having a Nowhere-zero flow is same as having a Nowhere-zero gamma flow for any group gamma of size 4. And G2 times G2 has size 4, so it's okay to work on G2 times G2 flow. But what is G2 times G2 flow? Well, I mean, you have all these 4 group values, right? So if I look at the entries with the first coordinate 1, then it's gonna be circulations, right? We will get 1 circulations, let's say phi 1. I mean, this is only remark. Phi 2 is the second coordinate of a fixed nowhere-zero. So, I mean, what I mean is, if I have a nowhere-zero G2 times G2 flow, then if I look at the first coordinate of this flow and the second coordinate of that flow, then both of them are the G2 circulations of G. And the property we want is that phi 1e is non-zero or phi 2e is non-zero for every edge. That is what we mean by nowhere-zero flow, right? So this is what we want. Okay, so we want, so it's enough to find 2 G2 circulations, phi 1 and phi 2 of G, such that phi 1e is non-zero or phi 2e is non-zero for all edges e in the graph. Right. So that's what we want to do. That's what we want to do. All right. Now, by Nash-Williams, G has 2 spanning trees. T1, T2, such that the intersection is empty. Right. Now, now we have a T1. Let's say this is T1. For any edge outside, I can find the cycle using E and edges on the T1. This cycle is called the fundamental cycle with fundamental cycle of E with respect to T1. All right, because that's a unique cycle. All right, so let me write it down. So for every edge E, there is a unique cycle CE in T1 plus E. Right. Now, what we're gonna do is to add all these things by symmetric difference. What does that mean? That means right. So is this notation? I'm summing by the symmetric difference for all edges of G not in T1, the set of edges in this. Let's say this is x1. Okay, so you may have other cycles, right? And then we take a symmetric difference. We are adding them together. Then x1 contains every edge outside of G, outside of T1. right? Because every edge outside of T1 appears exactly once in this list. Because the CE never contains two edges of, CE only contains edges inside T1 except E, right? So, the other way around. So this is, yes. And furthermore, X is a symmetric difference of Eulerian subgraphs, right? I mean, in EC1, every vertex has even degree, so you take a symmetric difference of that. Every vertex still has even degree. That means for every vertex, the number of, the degree in, the number of edges instead with the vertex is even. So let me say just say X1 induces an Eulerian subgraph. So let phi 1 E be 1, 0 if E is in X1, E is not in X1, then it's 0. Then phi 1 E. Phi 1 is a circulation. It's G2 circulation. Of G such that phi 1E is non-zero if E is not in T1. Similarly, there is a G2 circulation. So you do the same thing for T2. Right? So I have two circulations now, phi 1 and phi 2. And one of them is non-zero outside of T1, another one is non-zero outside of T2. So that means phi 1 E is non-zero or phi 2 E is non-zero for every edge. Okay? So phi 1, phi 2 is a G2 times G2, Nowhere-zero. G2 times G2 flow. That's it. That's the proof. Right? So it's a beautiful proof just by using Nash-Williams theorem, and the fact that you have two spanning trees will imply that you have Nowhere-zero full flow. So 4 is a nice number because 4 is 2 times 2. And Nowhere-zero G2 circulation is easy to deal because you don't need the orientations. Right? You don't have to orient edges because 1 is equal to -1. So therefore, when I talk about Nowhere-zero circulations, G2 circulation, it's convenient, right? There's no need to worry about incoming or outgoing. So G2 times G2 flow is also convenient because, again, -x is equal to +x. All right. So that's the first theorem that we discuss. Let me show you the second theorem. In the same paper, by using exactly the same method, he proved that every graph with no cut edge has a Nowhere-zero A flow. Isn't that amazing? So why 8? The proof method will require 2 times 2 times 2. So we are building G2 circulations. So if you build the 3 G2 circulations where every edge has at least one non-zero entry, then you get Nowhere-zero G2 times G2 times G2 flow. And that will imply that there exists the Nowhere-zero 8 flow. So that's the idea. And proof is similar, but now we don't have a high connectivity. How do we get 3 spanning trees? All right. So here's the idea. So let's do the induction on number of edges. So if G has an edge cut of size 2, so I want to increase the edge connectivity. So if I have a small edge cut, what should I do? I should say what to do. Yeah, if I have an edge cut of size 2, then we contract one of them, one of the 2 edges, say F out of EF. Okay. So by induction, by the induction hypothesis, G contract F has a nowhere-zero A flow. Okay, let's say nowhere-zero G2 times G2 times G2 flow. It doesn't matter, right? G2 times G2 times G2 has size 8, and by Tut's theorem we know that having nowhere-zero A flow is same as having nowhere-zero G2 times G2 times G2 flow. Now, if you contract it, what you end up is this. Now, let's say this is phi prime, and let phi of x to be phi prime of E if x is equal to E, and phi prime of x if x is not equal to E. So I'm extending everything by the same logic, except I will copy. Oh yeah, so this is. I will copy the value for this to here. So if you send something over here, I'm gonna send the same amount over here. And it's easy to see that phi is a nowhere-zero G2 times G2 times G2 flow of G. Why? Because I just need to check whether every vertex satisfies this flow condition. But remember, there's one observation you can easily make, that so the flow condition is that for every vertex, the sum of incoming edges is equal to sum of outgoing edges. By definition, you have to check it for every vertex. But actually, you don't have to check it for every vertex. You only need to check it for all vertex except one. If every other vertex other than my particular vertex satisfies the flow condition, the last vertex will have to satisfy the flow condition, right? If I have one vertex here, if every vertex has same number of same sum for incoming edges and outgoing edges, then when you add them together, then you end up with the same number of incoming to the outgoing to V. So as long as you satisfy this flow condition for every vertex except one, then you satisfy it automatically for the last vertex. And here, so every vertex other, let's look at every vertex other than, no, why did I say that? Maybe I don't have to say that. Yeah, so for each of these vertices, everything is the same, so nothing to worry. What about this vertex? Right, what about that vertex? Now, do we have a same, like the amount of outgoing is same as that? Well, that's how we choose. Oops, that's how we choose this value. It's same as that. The reason is every other vertex has same sum of incoming and outgoing, and I am adding, right, this thing and this. So inside this set, I'm adding sum of incoming, sum of outgoing. Then that has to be 0. And if that's 0, then this vertex will have the property that flow condition is satisfied. So I just made sure that this cut will make a 0. So this is outgoing, incoming. So this will make sure that this minus that is 0, right? And that will imply that this vertex will satisfy the flow condition. By symmetry, that vertex will satisfy flow condition. All right. Maybe I didn't have to say that all but one vertex need to be checked. All right. So as long as you have a large cutoff size 2, you can easily contract and win by induction. And this is true in general. Okay, true in general. If you want to prove the Nowhere-zero 5-flow conjecture, you can assume the graph is 3-edge connected. Right? Now, if I wanted to have 3 spanning trees, but the connectivity is only 3. What should I do? Let G tilde be the graph obtained from G by doubling every edge, by doubling every edge. So if I had an edge, then I will make 2 edges. Okay, if this is G, then this is G tilde. So why is it a good method? Well, the thing is, then G tilde is 6-edge connected. So G tilde has 3 edge disjoint spanning trees. By Nash-Williams, right? If you put K to be 3, then if you have a 6-edge connected graph, then you must have a 3 edge disjoint spanning trees. Now let's go back to our original graph. That means G has, so I will score, right, if T1 uses this one, and if T2 uses that one, then in G, I will have T1, T2 both using the same copies, right? So G has 3 spanning trees, T1, T2, T3, such that now no edge is used more than twice. So that means no edge appears in all 3 of them. So what that means is ET1 intersection ET2 intersection ET3 is empty set. All right. Now we use the same methods. Let phi I be a G2 circulations of G such that phi I is non-zero if E is not in Ti, right? And such a thing exists because, I mean, you look at the, I mean, if you remember the previous theorem, there's a construction, right? We just take the symmetric difference of all fundamental cycles, and then you put 1 if it's in that symmetric difference and 0 otherwise, and that will give me this. Then phi 1 comma phi 2 comma phi 3. When you combine them, is a Nowhere-zero G2 times G2 times G2 flow. Why? Because for every edge, it doesn't belong to all three of them at the same time, so it, right? Because intersection of all three spanning tree edges is empty. So that means it's gonna be like for every edge E, either phi 1 of E is non-zero, or phi 2 of E is non-zero, or phi 3 of E is non-zero. So this will never be zero. So graph has Nowhere-zero G2 times G2 times G2 flow. Okay, so that's a flow theorem. Right, so JJ's A flow theorem is a weaker version of 5 flow theorem, which is implied by 5 flow theorem, right? Yes. So even though we couldn't say that A flow is implied, but we are able, no, even though we couldn't say that 5 flow is enough, but we can already say that A flows are enough. Now, this was in 75 and the paper is very short. Now I will show you the theorem of my PhD advisor in my 81, which says that every graph with no cut edge has a Nowhere-zero 6 flow. So instead of 8, so let me move this. Oops, no. There's a better theorem. Right, 5 flow theorem. 5 flow conjecture implies similar 6 flow theorem, and this implies that 8 flow theorem, right? Oh, maybe I shouldn't add this edge. Right. Yes. Right, so this one has slightly more complicated proof because now we are talking about 6. 6 is not the power of 2, right? 6 is 2 times 3. So you can imagine that you, on one side you get the G2 circulations, and the other side you get G3 circulations. And when you combine them, you may get the Nowhere-zero 6 flow. And that's the idea. That is the idea. Now, the proof is a bit tricky. I will probably make this as a homework. So, I mean, one lemma. So write JBA 2 connected, no, 2 edge connected. Graph with the vertex v of degree at least 4, and let E1, E2, E3 be edges incident with the V okay, I should say non-loop edges. Non-loop edges incident with the V. Oh man, that's okay. I should say maybe let's focus on loopless graph. That will be simpler. For nowhere-zero flows, I don't care about loops because whenever I have a loop, I can delete a loop and apply induction. Right? And let U1, U2, U3 be the ends of E1, E2, E3 other than V respectively. So what's the situation? You have a vertex V of degree at least 4. You have a 3 vertices U1, U2, U3. And what we want to do is actually find the shortcut. Then, okay, so if G delete E1, delete E2, delete E3 is connected, so when you delete all three, if that is connected, then G delete E1, delete E2 and add U1, U2, or G delete E2, delete E3 plus U2, U3 is 2 edge connected. So what that means is, in that case, I can delete these 2 edges and add a shortcut. This or I can keep this, adding this, or that. Yeah, so red edges are removed. So one of these two will be 2 edge connected. That's the theorem, and this will be a homework problem. It's a nice application of this submodular property. All right, so why is this useful? If, for instance, if this one has a nowhere-zero k-flow, then I can use that to say that this also has nowhere-zero k-flow, because instead of sending this some value over here, I send over these 2 edges, right? If this has nowhere-zero k-flow, I can reroute this by using these two edges. So this is useful, right? As long as these two have a nowhere-zero k-flow, then this will have nowhere-zero k-flow, and we win by induction because this has a 1 less edges. As long as one of them is 2 edge connected, I can apply induction, and since we are trying to prove the nowhere-zero, our hypothesis is that every graph is no cut edge, so 2 edge connected graph has nowhere-zero k-flow, so this will be the one, right? So let's prove the seamers. So we may assume G is 2 edge connected. The statement itself says the graph has no cut edges, but then we look at its component. If component doesn't have an edge, then nothing to worry, so we can delete it. And so of course I want to write induction on number of edges. If component does have edges, then it cannot be a cut edge, so it is 2 edge connected. And if every component has Nowhere-zero k-flow, then all graph have Nowhere-zero k-flow, so we can assume the graph is 2-edge connected. And we may also assume G has no loops, because if you have a loops, then you can delete it. Right. And we can also assume that G is 3-edge connected. This is again by the same logic. If you have 2 edges, let's orient this way, and then it happens if you contract one of them, right? We have seen the same argument, and if this will have no cut edges, because we contract. And if it does have a cut edge, then in the beginning, in the previous graph, we will have cut edges as well, right? If you have a cut edge here, then this will have a cut edges. This will not happen. So we apply induction. So this new graph will have a Nowhere-zero k-flow. So that means this one has Nowhere-zero k-flow. So as long as you have the cutoff size 2, I can win by induction. So we have no edge cutoff size 2. All right. Now, of course, there's an issue about orientation, but having a Nowhere-zero k-flow for particular orientation implies that it has Nowhere-zero k-flow for every orientations. I can choose any orientation I like, so I choose these two on the opposite directions, and then I can give the same value, right? As long as this one has some value, then I copy that over here. All right. Now, what are the other assumptions? We can assume G is simple. Why? Suppose not. So let's say EF parallel. Let's delete E. Now, even if I delete, this is 2-edge connected because nothing changes, right? So G delete E is 2-edge connected. So it has a Nowhere-zero 6 flow. By induction. Now, if it does have Nowhere-zero 6 flow, how do I add E? Right? So for instance, let's imagine that this has a value 1. Now what should I do? Oops. What I can do is, it's not difficult, right? So if this was, I add 1 and 1. How about that? Right? So if I just make this cycle, right? So I can add some epsilon. Let me first orient E and F in the opposite directions. If E is here, then F is here. And as long as I have so G delete E has Nowhere-zero 6 flow, that means G delete G okay, let me say that G has a Nowhere-zero G6 circulations, right? So I have 2 edges directing opposite direction, and as long as I have a G6 circulation, here is a cycle of length 2. I can add some value epsilon on both edges. So epsilon could be like 1, 2, 3, 4, 5, right? And I mean, in one of them, I might have trouble because maybe the phi of E could have been -1. So if I add them together with 1, it could be 0. But for all other choices, I'm fine, right? For all other choices, I will make a phi of F. So if this is phi, then I have phi prime. X is going to be phi x or phi x plus epsilon. Epsilon is an integer, sorry. If x is not in EF or x is in EF, right? And one of them, some choice of epsilon. Actually, there are like 4 choices of epsilon, which will make this to be a G6. Nowhere-zero. Oh, no, I should say Nowhere-zero, yeah. Nowhere-zero G6 circulation. So this kind of idea will be used later too. We want to find the small cycles, and then by rotating along this cycle, we want to make sure that all the new edges will have non-zero values, while making sure that the existing ones still keep non-zeros. All right. So that's why we can assume that graph is simple. So this is the proof that we can assume the graph is simple, right? What we do when we have parallel edges, we can apply these reductions. All right. Now, this next claim, we may assume that G is 3 regular. There's no vertex of degree larger than 3. So suppose not. Suppose degree V is at least 4. Alright. So let's say E1, E2, E3, E4 are the edges incident with it, and U1, U2, U3, U4 are corresponding neighbors. And we know that G is a 3 edge connected. Now, graph is 3 edge connected. No, I claim that G delete E1, E2, E3, or G delete E2, E3, E4 is connected. Why? 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 So imagine that, suppose not. So this is a partition for E1, E2, E3. So E1, E2, E3 crosses this cut, right? So all the edges except E1, E2, E3 are on the left hand side or right hand side. And let's say this is crossing for E2, E3, E4. Alright, so that also, when I delete E2, E3, E4, I can partition graph into 2 parts. Right. Now, so what does that mean? That means now by symmetry, let's say E1 is here. I mean, I can say that, right? E1 crosses this cut, the vertical cut, but not horizontal cut. How about E2? And by symmetry between left and right, I can say that E2 is somewhere here. But, of course, E1 and E2 shares a vertex V. Oh yeah, so actually I can write V here. So this is E2. Why is this neighbor here? Because they cross this way, right? How about E3? E3 is also here, right? Because E3 crosses both sides, and E4 is here. Now what's happening? Now there are no other edges crossing these vertical cuts or horizontal cuts. Let's look at this cut. We have only two edges crossing this cut. So that's contradiction to the three-edge connectedness. Okay. So this is for any pair of edges, you have a cycle. So in other words, everything is given on the previous relation except the roots. The last condition is for any pair V, W, vertices right? So this implies that by the lemma, we can apply this lemma. One of these three will be two-edge connected, right? Either first case source, so G delete E1 delete E2 delete E3 is connected, so that implies that one of these two will be two-edge connected, or G delete E2 E3 E4 is connected. That implies that this or that is two-edge connected. But in all cases, one of these three graphs will have Nowhere-zero 6 flow. So graph G has Nowhere-zero 6 flow. So we win by induction. So this proves that we can assume the graph is three-regular. Okay? Now so far we only try to assume many things. And this works even if we replace 6 by 5. Which means that if we want to have if we want to prove a 5-flow conjecture, it's enough to assume the graph is three-regular, three-edge connected, simple, right? And three-regular and three-edge connected graph has nice property that actually they are three-connected. Why? Because if it's not three-connected, you cannot have a vertex cut of size 2, right? But since it's three-regular, it may look like one of these three, right? But in all cases, you can find the cut of size 2. So that's why it's three connected. And of course, you may have to check carefully. You might have a cup vertex, and what should we do? I mean, if you have a cup vertex, you can find the cut edges, right? So graph is three-regular, three-connected. So we may assume G is simple, three-regular, three-connected. Okay. Now now we're gonna have a interesting technique. All right, so okay, maybe I will continue from here in the next lecture. Right. So far, in order to prove the seamless theorem, we show several reductions by applying induction on number of edges, that the graph is right. By these reductions, we can assume the graph is simple, three regular, and three connected. So in the next lecture, we will complete the proof starting from here. All right. Okay. So that's it.